Yeah, I didn't say. My name is Kate. We will have today like two practical sessions. They are not like really practical because we will solve theoretical problems without computer. So you don't need computer. Like you need computer only to look at the problems. The problems are on our GitHub. You have a link in your brochure, but also you may use this short link. This is a link for the problems for the first seminar. You also have, these slides are also on GitHub, so you can find them there, okay? 1 minute for everybody to find the problem set. May I continue? Okay. The format will be the following. We will have several problems. I will give you some time to try to solve them by yourselves. And like in 10 minutes, we will discuss the solution. Okay? If you have any question, please don't hesitate to raise your hand and ask a question. You have me, and you also have Pavel and Andrew, who will help you. Okay? The goal today is to really understand the main concepts. So if you like don't understand something, ask about it. Okay? Okay. This is the first task. You have like, I don't know, 7-10 minutes to solve it. Okay? So who already finished? What? One, yeah. That not everybody has the file, yes. We are trying to solve the problem, I mean, with the file. So we will go one by one. Should we continue? Should we discuss the solution and go to the next one? Yeah? Okay. So, this problem is, let's first discuss the mathematical formulation. So here we have two random variables, x and y. Both of them are binary. The first one corresponds to the Dark Lord, so it's equal to 1 if the Lord is dead, is alive. And the second one corresponds to the dark mark, so it's equal to 1 if the mark is still visible. And on the slide you see the formulation of the problem in formulas. So we have conditional distributions of y given x, and we have our prior on x. And we want to compute the probability of x equal to 1 given y equal to 1. Okay? Okay. What should we use here? Bayes rule. Yeah? So we just use Bayes rule, and that's the answer. Do you have any questions? Do you have any questions, or is it clear and we should continue? Okay, let's continue. So now we discuss the problem about a dice. So it's very similar to a problem with a coin, which we discussed at the lecture, I think. And the problem is you have a dice, you have several rolls, you roll it several times. And you want to estimate the probability of the dice to go down on the side k. So we will solve this problem in two ways, in frequentist way and in Bayesian way. So in frequentist way, we just want to compute maximum likelihood estimate for theta. And in Bayesian way, we will compute a posterior distribution. Let's start with frequentist way. Okay? Should I leave this slide, or should I go to the PDF? I think PDF, I'm worried that PDF is very large for this problem. Oh no, it's not very large, it's okay. So the problem number 2. Small disclaimer: what should we use if we have if we know that our theta is from simplex? How should we optimize it? Lagrange multipliers. Yep. Okay. Okay, let's discuss the solution. Okay. So here we have theta from simplex. So we have two types of restrictions. The equality restriction that sum of theta is equal to 1, and inequality restriction that all thetas are more than 0. Okay? So to deal with inequality restrictions, we may just reparameterize our model and say that instead of theta, we will use mu, which is equal to log of theta. So mu is from R, so we don't need inequality restrictions. Okay? Is it clear? Okay. Now to deal with equality restrictions, we use Lagrange multipliers. So we write down Lagrangian, which is equal to the function which we want to optimize minus Lagrange multipliers times our restriction. And now we differentiate our Lagrangian with respect to both mu k and Lagrange multiplier. Makes both of these derivatives equal to 0 and find the solution. I will give you like 1 or 2 minutes to read the formulas. Do you have questions? You're very shy and don't want to ask questions. That's bad. I mean, our goal is to understand the main concepts. I want everybody to understand them. Yeah. Yeah. Kate will help you with mic. Which doesn't work.
Yeah, it works. Does the denominator, the last denominator, exactly equals the n?
The denominator, which one? This one?
No,
this
no. Yeah.
This one?
Yeah.
And what's the question?
Does it exactly equals to the n, right? Yes. Okay.
Yeah.
Okay, thank you.
Sorry, I don't exactly understand the first line, like how you're able to go from an inequality constraint to an equality constraint.
It's not going to from inequality constraint to equality constraints. It's like we reparameterize our model to just drop the inequality constraints out of the window. You may just write the second Lagrange multiplier for inequality constraints. It will be okay. You will have the same answer. Or you may do it like this.
Okay.
I didn't
No,
help.
sorry, I don't follow.
It's like theta. Yeah. Yes. Like theta is more than 0, but in this reparameterization, mu is from R, so you don't need constraints for mu.
Okay, thanks.
The second part of last equation, so lambda disappeared. Then how could you get lambda then?
From the first line, actually. So this sum is equal to 1. So you sum up these terms, and here you find lambda. Okay? Like at the first line with derivatives, at the end you have lambda. So you may sum up exponents of mu, and then derive lambda from this formula.
I see. Thank you.
Okay? Any more questions? because we don't want to deal with inequality constraints. Okay, last question.
The condition that derivatives are zero is not sufficient for minimum, yes?
Yes.
How do we get sufficiency?
Yeah. Like second derivative, I think. But we will not do it.
So,
if you want to, we may do it after the seminar on the board. I don't have slides for second derivative. Okay, let's go to Bayesian framework. So in Bayesian framework, we need some prior for theta. And the good prior for theta is Dirichlet prior because it is conjugate to our multinomial likelihood. So, and conjugacy is good because if we have conjugacy, we may use full Bayesian inference and have analytical formulas and don't worry about integrals in the denominator. So the task is to first check that our prior and likelihood are conjugate, then do Bayesian inference, and then we also have two more points. The first one is to compare the result of Bayesian inference and frequentist inference, and the last one, if we will have time, and we will not. The last one is your homework, if you want to. So I will open the PDF. Yes? Yes? No? Yes. I will do it like this, since we need likelihood at the formula 1. And guys, as one of you pointed out, we didn't discuss what is Dirichlet distribution. So let's, it's a little bit late, but let's a little bit discuss it. Like, 1 second. Dirichlet distribution. It's like beta distribution, but on simplex. So beta distribution is over the one variable from 0 to 1, like the over simplex with 2 points. And Dirichlet distribution over simplex with many points. It may have two main forms. The first one is like on the slide, so it has big values in the middle, and the probability have big value in the middle of the simplex, and small values on the edges of the simplex. And there is a second one, then the probability is low on the middle, in the middle of the simplex, and high in the edges. So why is it good? Because you may use this distribution to say that you want a sparse solution or not sparse solution. So in the case of the dice, if your distribution is like this, then your dice is like normal dice. If your distribution looks like this, so it's a low probability in the middle, then it's very strange dice with, for example, I don't know, on each side you have 1, or something like this, okay? It's like with a coin, if you think not about the dice but about the coin, then this distribution with low probability in the middle says you that your coin is like somebody wants to lie to you and give you a coin which is not right. So let's discuss first 2 points, okay? Or you need more time? Who needs more time? 1, 2, 3. 1 minute, and then we will discuss the solution for first 2 points, okay? Guys, unfortunately, our seminar ended 5 minutes ago, I think. So let's discuss the solution, okay? First, let's check that likelihood and prior are conjugate. To do so, we look at our probabilistic model. So our probabilistic model says us that we have a prior on theta and our likelihood x given theta. And to check that prior and likelihood are conjugate, we need to write down prior, write down posterior, and understand that they are from the same family, or functional family. So our prior is P of theta. It's a Dirichlet distribution. As a function of theta, it looks like this. So we have C and beta are some constants. We don't care about them. So this is a function of theta, okay? And our posterior distribution is proportional to the products of likelihood and prior. So we write down this product and see that the functional form is the same. Only constants are different. Do you see it? Okay, so our prior and posterior have the same form, so our prior and likelihood are conjugate. If our prior and likelihood are conjugate, we may use full Bayesian inference. So we use Bayesian rule, Bayes rule, and since our likelihood and prior are conjugate, we don't need to compute the denominator, so the normalization constant, because we already know that our posterior will be Dirichlet. It's the same as prior, okay? So we just need to compute new parameters of a Dirichlet distribution. To do so, we write down the formula for posterior, which is proportional to product of likelihood and prior. We write down this formula, see that this is 1 divided by beta function is a constant. We don't care about it. And we just use the theta to the power of nk and theta to the power of alpha k minus 1. And see that this is a Dirichlet distribution with new parameters which is, that are equal to alpha plus n from 1 to k. Is it clear? Okay. Do you have any questions? You want to a free time, yeah? One question.
Denominator in the Bayes formula is P probability of x.
Yep.
It is constant. But what this constant is equal to?
The point is, if our prior and likelihood are conjugate, and then we know this constant from the formula of the standard formula for our posterior. Here we know that our posterior is Dirichlet distribution. And our posterior distribution is proportional to this thing, yes? If it's proportional to these things, then we can normalize it by taking an integral of this thing, yeah? We just don't want to do it because we already know that this is Dirichlet distribution and we know the formula for normalization constant of Dirichlet distribution from Wikipedia. If you compute the integral of this thing d theta, you will have the same thing, the same normalization constant as in Dirichlet distribution, like beta function, like this beta multivariate beta function. Okay, and also we see that if we compute the expectation of our posterior, of our Dirichlet distribution, we see that this expectation is similar to maximum likelihood estimate in the sense that if we have a small k, so we have a small number of objects in our likelihood, then our estimate is mostly from prior, because nk and nl are small. And if we have a lot of data, so we have large k, then Bayesian estimate and maximum likelihood estimate, they are almost the same. Yeah? because nk is much bigger than alpha. Yeah. It was a mistake. You may compute mode or expectation. The logic with this thing that Bayesian estimate is similar to maximum likelihood estimate if you have a lot of data will be both with mode and with expectation.
Okay. So when do you use which? Mode or expectation? Are there any guidelines?
What do you mean?
No, you could use either the mode or the expectation,
You may
right?
use whatever you want. It depends on the task. What do you want from your the final answer?
Okay.
Okay, and the last part will be your homework if you are willing to do it. Or you may do it like after the school. Or you may not do it. It's up to you. Okay, now you have like a break, like 3-minute break. Will we give them like at least 7 minutes? 7 minutes. Okay. And then you will have the second lecture.